nanoHUB.org.
Online simulation, and more for nanotechnology.
Welcome everyone to a new workshop in our series on hands-on workshops on machine learning. I'm very excited to introduce Dr. Saaketh Desai. Saaketh is going to tell us about parsimonious neural networks. He's a computational material scientist. He's a postdoc at Sandia National Labs at the Center for Integrated Nanotechnologies, CINT. He got his PhD last year in material science from Purdue University, and his undergrad degree in also material science from IIT Roorkee in 2015. And you're going to see what Saaketh's interests are during the talk. So without further, one more announcement. Let's use the Q&A to ask questions. So if you have questions, write them down, and I will go over them. And when Saaketh finishes, I'll try to highlight some of the key questions that went unanswered. So thanks everyone for participating. And thanks so much to Saaketh for running the workshop. Take it away, Saaketh.
All right. Hi, everyone. First of all, thank you for the introduction. And thank you, everyone, for showing such interest in this workshop and attending. Like Professor Strachan mentioned, I'm a new postdoc at Sandia, which means the work I'll be talking about today, which is parsimonious neural networks as a tool to learn interpretable physical laws, is something that I worked on towards the end of my grad school period at Purdue. And I'm excited to talk about the approach and walk through some code today and illustrate how this method works and how we can discover physical laws directly from data. And I wanted to start by talking about something we're all familiar with, which is the wide range of applications that popular machine learning models have. We're all familiar with or have heard of models that perform image classification, that detect objects when driving self-driving cars, that perform text translation, or that play video games, sometimes better than humans. While these models are very popular, the key takeaway for us for this workshop is that these models are built to excel when there is plenty of training data. So for example, the image classification algorithms can be trained on databases like ImageNet, which have 1 million plus images. Self-driving car ML algorithms are trained on databases like DeepDrive, which also have 1 million plus images where you are trying to detect different objects. State-of-the-art natural language processing algorithms that perform these kind of text translations shown in this picture are models like GPT-3, which have billions, I think 170 plus billion parameters. So you can only imagine the kind of training data that went into training such an algorithm. And if you think of reinforcement learning for playing video games or for other applications, the state-of-the-art algorithms learn by playing thousands of hours of games with themselves before they get any good. And so while these models are excellent at their job and are doing a really great service, they're also designed to perform well when the data is plentiful. Now, this is not always the case in science and engineering. They were limited by the expense required to collect a data point. That could be running an expensive computational simulation or running an expensive experiment. And so because of the time and cost factors, we may not have such large data sets at hand. So what we require from our ML models in this case is the ability to provide some sort of confidence and interpretability, because the data sets that we're working with are very small. So what we want from the model is to provide predictions which we have confidence in, especially when we don't have the copious amounts of data that we have, like in these models, to trust that the model has learned everything from the data. So when we're working with small data sets, we're hoping that the ML algorithm has some sense of interpretability to it so that we can have confidence in its predictions. And there are various ways of achieving this interpretability. For today's workshop, we'll be talking about parsimonious neural networks, which is a tool where we couple neural networks and genetic algorithms to balance interpretability while also having models that are accurate and perform well on a given data set. And to understand how we couple neural networks and genetic algorithms, it helps to start right at the basics with this picture of a generic neural network. In the parsimonious neural network or PNN framework, we start with a generic neural network. The inputs are x1, x2, all the way till xn, and the output, our quantity of interest that we wish to make a prediction for, is this quantity y. Now, in most standard neural network models, you can have multiple number of neurons in a single layer, and you can stack as many layers as you want. And the deeper you go, the deeper network you have, the more likely it is to make an accurate prediction in some cases. But in this case, what we're interested in is discovering equations from data. So what we do is start with the generic neural network that some of us have seen before, but make a small tweak to it, where we have each neuron have its own activation function. Now, this is slightly different from a conventional neural network where an activation function is associated with all the neurons in a layer. Our goal with introducing an activation function for each neuron is to allow a greater combination of functions and explore the search space better when we aim to discover this equation. So all the elements marked in red here in this picture, which is the activation functions for each neuron and the weight values in each of the layers, are marked in red because they are coupled to the genetic algorithm. And by that, I mean that the genetic algorithm decides the initial value for the weights and the activation functions for each of the neurons. And this allows us to translate this network into a list of numbers that we can call an individual, which the genetic algorithm can operate on. And we'll see how those operations are performed in a second. But the key aspect of coupling neural networks to genetic algorithms is to encode or translate this neural network picture to an individual. And we do that by assigning each neuron an activation function and the weight values being controlled, at least the initial values, by the genetic algorithm. The second thing that we need to do to couple neural networks with genetic algorithms is to assign a fitness score to each network or each individual now. And the way we assign a fitness score is by composing two terms together. The first term is an error on data term. This just tells us how well the model performs on the given data set. And we evaluate the model on the testing data set so as to avoid overfitting. The second term is the crucial term that allows us to balance interpretability and accuracy, which is a term that quantifies how complex the model is. And we do this by assigning a complexity score to each activation function and each weight, where we favor linear activations and simple weights over nonlinear activations and arbitrary weights that could be obtained when we train the model using backpropagation. So when we combine these two terms, we have a way of quantifying the complexity of a model. There are many other ways of doing this, but this is the way we have adopted in the PNN approach. To evaluate the error on data, we use standard backpropagation algorithms, which use the keras, and we use the keras package in this case. And to evaluate the parsimony and to perform all the genetic algorithm operations, we use the deep package in Python. So to see how that works, let's think about how we would train a PNN to discover equations from data. I said that the first step that we need to do is to encode this neural network picture into an individual, into a set of attributes or a set of genes that the genetic algorithm can operate on, and assign a fitness score to each individual or each network. So once we have that defined, we can build one of these networks, call that one individual, and then build many such individuals, each of which has their own representation as a sequence of genes, a sequence of numbers in this case. And we can call this collection of individuals generation 0. This is the population for the first generation of the genetic algorithm. And now we evaluate the fitness of each of these individuals using the error term and the parsimony term that I talked about a minute ago. And once we evaluate the fitness for each of these individuals, we can perform crossovers and mutations to generate new interesting individuals for the next generation. And we can select for the fittest individuals using a tournament-based selection where we select the top n individuals from the given set of individuals. So that way, the genetic algorithm, when it goes from Gen 0 to Gen 1, has a way of generating new individuals via crossovers and mutations, and a way of selecting the top individuals in a generation using the tournament-based selection, the fitness-based selection criteria. So what we do after this is we obtain this new generation of individuals. And this is generation 1. Each of these networks has their own fitness scores, which we have to compute using backpropagation and by computing the complexity of the model using the equations before. But when we repeat this for many generations, we hope to end at a fittest individual, and we end at this point based on the fitness-based selection criteria, which allows us to filter for fitter individuals. And at the end of n generations, our fittest individual is going to be a set of weights and activation functions, which we can then look at and write down the equation as an interpretable equation that relates the output y as a function of the inputs x1 to xn. And the reason we're able to do this is because the PNN scheme favors simple linear activations over nonlinear activations and weights of zeros and ones over arbitrary complex weights. And this helps us to concisely write down an equation given this pictorial representation of a network. So just a small word on crossovers and mutations. For those of you seeing genetic algorithms for the first time, this might seem a little non-intuitive. How does this apply to neural networks? So in a standard genetic algorithm, the crossover operation is designed to generate two new individuals by the following process. What we do is we combine a subset of the genes of two individuals and swap them between the two individuals. So in this picture, we have an individual A and an individual B. The subset of the genes that we are interested in crossing over are marked in red and gray. And what happens in the crossover operation is that the first individual receives the gray set of genes from individual B, and individual B receives the red set of genes from individual A. So we have swapped a subset of the genes. And this gives us two interesting individuals because the rest of the individual is the same. So we get to assess how this inserted gene subset helps the individual perform, and decides the fitness of that individual. Perhaps slightly simpler to understand is a mutation, where we pick a gene in the individual and randomly flip it to another gene. So in this case, a 1 becomes a 0. So what does this mean in the context of neural networks? I said we're going to apply neural network crossovers and mutations to neural networks. What that means here is that we're going to select a set of weights and maybe activations. In this example, I've selected some weights marked in red. And what the crossover operation is going to do is swap the weight values between the two individuals while keeping the rest of the network the same. Again, we have fixed weights and trainable weights. So weights of ones and zeros are kept fixed, and arbitrary weights that are initialized by random numbers are trained using the backpropagation algorithm. So when we perform this sort of a crossover operation, what we essentially have done is kept the rest of the network architecture fixed while we swap out certain weights and maybe activation functions. So this could lead to interesting individuals that could perform better on our data set. Perhaps simpler to understand again is a mutation. The simplest case of a mutation could be switching a weight of 1 in a network to a weight of 0. And again, since this weight is kept fixed, this network might perform quite differently on the dataset as opposed to the parent individual. And again, these operations are done using the deep package. The deep package is useful because it helps us to build custom genetic algorithms and allows us to perform all these coupling operations relatively easily, as you'll see in the code in a second. So the example that I wanted to talk about today is discovering equations that describe the melting point of a data, given some fundamental inputs. So the question that they're trying to answer is, if I have a set of materials and I have properties, basic properties such as the volume, density, moduli, can I predict the melting temperature? And one avenue to do this, which has been very popular since 1910, is the Lindemann melting law. This law predicts that the melting temperature of the material is going to be proportional to the square of the interatomic spacing, the square of the Debye temperature, and the mean atomic mass, where F is a fitting constant. And this law has been quite successful at predicting melting temperatures for various perovskites, as I'm showing here in this plot on the right. The melting temperature correlates very well to the Lindemann expression. But this Lindemann expression was developed using an empirical criteria regarding atomic vibrations. So what we were hoping is that our PNN scheme could discover improved melting descriptions just directly from the data without having to give physical insight about atomic vibrations. All we have is the data set and the inputs to our model. And the question that we're asking is, can we predict the melting temperature for these set of materials? So before we jump into the code, I just wanted to set up the problem a little more in detail so that we understand what's going on in the code. So I said that our data set has inputs such as modulus, volume, density, and so on. And as you might have seen in the PNN scheme, we are trying to combine neurons with various activations and weights, which means that we run the risk of adding a quantity like a volume to a quantity like density, which have two different units. So to avoid such phenomena, what we do is perform a standard dimensional analysis. And in this case, what that means is that we come up with these 4 inputs, theta 0, theta 1, theta 2, and theta 3, which all have units of temperature. So we combine the inputs in our data set to come up with units that have, quantities that have units of temperature. And once we have this, we then divide each of the inputs by theta naught to get us 3 dimensionless inputs. And now we can compare and combine these in any way without worrying about different units. So what the architecture for the PNN is that we have 3 inputs, the dimensionless quantities theta 1 prime, theta 2 prime, and theta 3 prime. And what we're trying to do in the code that I'll walk you through in a second is set up this kind of a simple parsimonious neural network, which has 1 hidden layer and 3 neurons, A1, A2, and A3, and that tries to predict the melting temperature. So to see how to do this, I would invite all of you to go to this link here, nanohub.org/tools/PNN demo, and you should come to a screen like this. And I request everyone to hit the launch tool button so we can start looking at the code and start developing our own models. I'll also do that right now. So if we go to nanohub.org/tools/PNN demo, and hit the launch tool button. If you haven't signed into nanoHUB, it will require you to sign in, so please do that. And what we'll see when the tool launches is a landing page that has a set of links to various Jupyter notebooks, like here. Each of these blue text lines is a link to a Jupyter notebook. So I'll just wait for a second for everyone to reach this page. And I request everyone to click on the 4th link here, designing a parsimonious neural network, predict melting temperature. So if we click on that notebook, we will launch the Jupyter notebook that develops this parsimonious neural network and discovers equations from data. So while I wait for this to load and while I wait for everyone to come to the same page as I am, for those of you who are seeing Jupyter notebooks for the first time or are not very familiar with this, Jupyter notebooks allow us to combine simple plain text with code in an easy manner. So we have cells in a Jupyter notebook that we need to run in order to run the code. And each cell can have plain text, like a markdown cell, or can have some Python code, like a regular code cell. And to run the notebook, we need to run each of the cells in the notebook. And to run each cell in a notebook, we have multiple ways. We can hit Shift-Enter to run a cell, or we can click this Run button to also run that cell. So just as an example, I'm going to go ahead and hit Shift-Enter on this first cell, and I'll explain what this does in a second. And for a brief second, there was a star there that showed that the cell was running. And now that I have completed the execution, I have this number 1, which tells us that the cell has executed. So I'll just, again, wait for a second for everyone to be on the same page. So I want to go to nanohub.org/tools/PNN demo and click on the 4th link in the landing page to land on this notebook and hit Shift Enter to run the cells. So assuming that most of the folks are here at the same page that I am, let's start walking through the code. The first thing that we need to do is import libraries. By using standard libraries such as NumPy and Pandas to deal with our data set, which is the CSV, and to deal with all the arrays that come about when we are processing these various networks and individuals. We're going to use the train test split function from scikit-learn to divide our dataset into training and testing datasets. And the most important imports are the Keras package to train neural networks. You'll notice that not only do I import Keras, I also import specific layers, because that's what we need to build this custom neural network where each neuron has a different activation function. And the second important import is the deep package, which allows us to encode this neural network as an individual and set up the genetic algorithm based on this individual. So perform all of the operations that I was talking on in the slides, the crossovers, the mutations, and whatnot. The deep package is what we'll use for that. So let's go ahead and run that cell again. The first thing that we will do is read in our dataset. The dataset is built into the tool. We added in as a CSV file. This file called combine data. And what we're going to do is use the pandas read CSV function to read in this dataset. This is very convenient because we often have Excel files or CSV files of datasets, and pandas has many different functions like read CSV and read Excel that we can use to directly import this into a data frame, which we can then perform easy computations on. So let's just go ahead and run this cell. You'll notice that I've printed these numbers here, 218 and 15, which is the shape of the data frame. And to understand what this shape means, let's go ahead and actually look at the data frame. So to do that, I ask everyone to click the insert option here and insert a cell below. That allows you to type your own code. And what we're going to do is display the data frame. And luckily for us, the command to do that is literally say display data frame. Data frame is called df here. So if we run that cell, you'll notice that it's printed the entire data frame for us. And you see the columns in the data frame. We have a materials project ID, the formula, density, bulk modulus, so on, and the melting temperature. So this number 218,15 tells us that we have 218 rows in this data frame and 15 columns. So we have 218 training data points. The next thing that we'll do, having read in this data frame, is to compute those dimensionless inputs that we need to set up our PNN. We said that we have inputs of different dimensions, so we will first compute quantities that have dimensions of temperature and then divide them with one another to get dimensionless inputs. So to do that, we're going to use these operations where this is where the power of data frames kicks in, because we can perform operations on an entire column of a data frame just by writing a single equation. For example, I'm going to define this quantity A as an effective interatomic spacing, and I'm going to compute that by taking the volume per atom and taking a cube root of that. Notice that we don't have to write any loops to compute this for all of the elements in the data frame, because such operations are already vectorized, and we can easily write this and it will apply to all of the rows in the data frame. So let's go ahead and hit Shift Enter on this cell. And the next cell is where we actually compute the dimensionless input. So as you'll see, we have lines here that compute theta naught, theta 1, theta 2, and theta 3 coming from these equations here. So these numbers that you see here are obtained when you swap in the values for h bar, Boltzmann constant, and other constants. So that's why we have such numbers, but the rest of the quantities are the physical quantities from our data frame. And having computed those theta naught, theta 1, theta 2, and theta 3, we can then compute the dimensionless inputs, theta 1 prime, theta 2 prime, theta 3 prime. We're also going to divide our output by theta naught So we're also predicting a normalized output. This allows us to limit the range for the model predictions and allows us to easily write the equations down once we discover models. So what we're going to do is set up an input array called inputs, where we declare that the inputs to our model are going to be theta1 prime, theta2 prime, theta t prime. And you'll notice this extra input called ones, which is just a vector with literally the number 1 in it. And the reason for this will become apparent once we build the actual model. But let's just go with this for now and think that we have 3 inputs, theta1 prime, theta2 prime, theta3 prime, and this extra input called ones, which we'll use in a second. The output is the normalized melting temperature, and we use the reshape command to shape the arrays appropriately. And what do I mean by shaping it appropriately? We'll find out when we run the cell. So you notice I've printed 3 shapes again. The first shape is the shape for the inputs and the outputs. If you recall, the data frame had 218 rows and had 15 columns. We've just computed 4 columns that we could use as inputs, and the output is just 1 column, which is the normalized melting temperature. And we have 218 elements of that. The next shapes are the shapes of the training and the testing datasets. And this is where we use the train test split function from scikit-learn. So we pass in our inputs and outputs and ask scikit-learn to divide 20% of this data randomly into a testing dataset. And we use the random state command so that we are able to reproduce this exact train test split every time we run it. If you do not specify this keyword, every time you run this, you'll get a slightly different split between the training and the testing sets, as different elements are randomly chosen to be put into the test set. All of this means that from the 218 data points we have separated out 44 data points to be in the test set and 174 to be in the training set. And that's all we need to do to process the data. Now we've built our inputs to the model. Now we actually need to build that model, build that complicated picture that I showed in the slides. To do that, we need to define the list of activations that each neuron can take up and the list of possible weights. So we're going to do that using Python dictionaries. So Python dictionaries, for those of you who are relatively unfamiliar, we have a keyword and a value. So a key of 0 means that the activation function is linear. Key of 1 means that the activation function is x squared, and so on. We do the same thing for the weights. A key of 0 means that the weight value is 0. A key of 1 means that the weight value is 1. And a key of 2 means that the weight is going to be arbitrarily initialized to a random value between -1 and 1. And when we initialize this weight arbitrarily, we can then use the backpropagation algorithm to compute the weight that we need, given the other weights and given the other activations, to best fit the data that we have. So think of 0 and 1 as giving us weights of 0s and 1s. They are fixed. Think of the key of 2 to be a way to say, I don't know what this weight value should be. I'm going to initialize it as a random number between -1 and 1. The backpropagation is going to tell me what the value for that weight is going to be. So let's go ahead and hit Shift Enter and run this cell. And I'm going to just take a brief pause and review what we've just done. We've read in our CSV dataset, split it into training and testing sets by using the train test split function, and also computing the 3 dimensionless inputs, theta1 prime, theta2 prime, and theta3 prime. The next step is the actual interesting step, where we're going to go ahead and build this model here that I show in the slides, this neural network with the custom activations and all of that. So how do we do that? We're going to build this neural network neuron by neuron. So let me explain that by switching back to the picture here. We want to build this kind of a network. What we're going to do is build the neuron A1. What do I mean by that? As you can see, A1 is connected to all of the 3 inputs and has its own activation and its own associated set of weights. So we're first going to build that neuron up, like connection by connection. So we're going to describe this connection first, this connection next, and this one last. And we're going to build neuron A2 in a similar way, neuron A3, and then we'll build the neuron, which is the output neuron. So I'm saying this beforehand because that's what the code flow looks like. So if you go back to the code here, The first cell describes some of the custom activations that we need. The Keras library has many useful activation functions for us, like linear, tanh, and so on, but it doesn't have every activation under the sun. And in this case, we want the unique activations x squared and 1 over x. So we're going to define that using these functions. So let's hit Shift Enter on that cell to run that. And this is the function create node, where we're going to create that neuron. So let's understand what this function does. We said we are going to build this neuron by neuron, connection by connection. So let's skip over to the main lines here, these 3 lines that I've highlighted. The dense command is used in Keras to declare a dense layer, that is a fully connected layer, that takes in the input specified here as input 1 and applies this dense operation to give us the output, which is in this case AN1. The 1 number in this dense tells us that we want a dense layer with 1 neuron. If you switch this 1 to 100, this means that you want to connect input 1 to the output AN1 by using a layer of 100 neurons. So the dense command is used to set up a layer of neurons in Keras. We are going to set up a dense layer with only 1 neuron. The reason we do this is because we want to build each neuron connection by connection. So if I wanted to translate this line and write it down a little simpler, what I would say is that what this line is doing is saying that AN1, which is an intermediate quantity that I'll compute, is some weight times input 1. Sorry, input 1. Input 1 is theta 1 prime that we computed a few steps above. So that's what this line does. And what does this line mean? This line is representing this connection here, that A1 is some weight times theta 1 prime. Now it's also some weight times theta 2 prime and so on, but we're going to build that up step by step. So that's what this line does. The second line is very similar. The input is now input 2. We again use a dense layer with 1 neuron, and we say the output of that is going to be stored in AN2. So what this line effectively does is it says AN2 is going to be equal to some other weight times input 2. I hope that makes sense. The third dense command does the same. And you might be wondering, why am I going through all this process? Why couldn't I just write this equation down? It's because when you're defining neural networks or layers in Keras, you are expected to work with the tensorial representation of the objects. You can't assume that you have a data set or a data point in your hand. Everything has to be defined using tensorial operations. And when you feed the data into the model, the model will know how to deal with the data and perform the operations on it. So you cannot assume that you have data in your hand and you need to work with the raw tensor notations, which is why we use this kind of a notation to write down this simple equation. And why are we computing all of these intermediate quantities, AN1, AN2, A3, AN3? All we need is this value, right? We need this value A1. So let's think about how these values are computed in a regular neural network. If I gave you a standard neural network and asked you, what is the value of the neuron A1? You might say, well, A1 is going to be a linear combination of the weights times the inputs. So weight times theta 1 prime plus weight times theta 2 prime plus weight times theta 3 prime. Plus a bias if you have a bias. And the activation function applies to that sum. The activation function could be linear, it could be tanh, it could be whatever you want. So we're going to do that same thing, except we're going to build up step by step. And the reason we do that is because this allows us to add in more complexity when we consider different kinds of activations. So given that we've computed these intermediate quantities, let's go ahead and jump to this else block here because this is easier to understand. The first command here is an add command where we are adding everything in this quantity node list. Node list is the list of these intermediate quantities that I've computed. So what does this line do? This line tells us that AN, which is the output of the add operation, is a sum of AN1, AN2, and AN3. Which is just this. I'm going to write it out explicitly. That's what this line does. And to treat it like any other neural network, what we need to do is apply a bias if we have any. In this case, we don't. And apply the activation function to it. So what we're going to say is that if the activation function is x squared, apply that activation using the Keras keyword for activation that applies the squared x squared activation on this output. So what this line does is it says, well, an is actually an squared because the activation is x squared. And if the activation function is in inverse, we're going to say an is 1 over an. And if you have any other generic activation like a tan H or a linear activation, you're just going to say an is the activation function applied to this quantity an, which is the sum of the node lists. So let's take a step back and understand what we've done. We computed 3 intermediate quantities, an1, an2, and an3. And what we've done in this step is to say an is going to be an activation function applied to this quantity an, which is the sum of the node list, which is an1 plus an2 plus an3. And this is exactly what a normal neural network would do. The reason we've spelled it out in such explicit detail is because if we want to consider an interesting activation function, like a multiplication, this equation isn't true anymore. So by default, what Keras would do is this, and this wouldn't work if I said I wanted a multiplication. So how would we do a multiplication? Well, what we want to do is multiply the 3 quantities, right? So you might think what we want is to say an is an1 times an2 times an3. And that's kind of what we want, except there's a slight subtlety to this, which is that if one of these quantities is 0, we have complete freedom in choosing the other 2 quantities in any way, and the product is always going to be 0. And this can put the optimizer in trouble. So to avoid such situations, what we're going to make the small change to this equation is to say, multiply only the non-zero quantities in these terms and only multiply them. So if an1 is 0, let's ignore that and multiply an2 and an3. If all 3 of them are 0, then the output is 0. If none of them are 0, then we can just multiply all of them. So that's what this if block performs. And I'm not going to go into all the details of that, but I hope you understand the intuition. A, behind setting up this kind of multiply activation function, and B, the reason for building up this node from scratch, as opposed to using a straight neural network from Keras, because we want to be able to specify these interesting activations. So for example, if you wanted to specify a power law activation, you could add in another block that says, compute the sum of the quantities and take a cube root of that, for instance. So the create node function builds each of these neurons step by step. I hope that's clear. Let's run this cell. I remember that we are all defining a lot of functions, so you won't see any outputs just yet, but we'll see the outputs when we actually call all of these functions together. Now that we've created each neuron, we can create the model, and we're going to use this using the create node function that we just defined. So let's skip over to these 4 lines here that declare that our inputs, input 1, input 2, input 3, input 4, are input neurons. This way, Keras knows that these are inputs and expects them to be of a certain shape. And when the data is passed into Keras, the inputs are passed into these tensors automatically. We're now going to use the create node function to create the neurons A1, A2, and A3. And this function call builds all of that connections, adds them up, does the multiplication, does whatever is needed to compute the value for neuron A1. There's a lot of arguments to this function. The main arguments are the 3 inputs, obviously, the name of the neuron, and a list of flags that indicate whether a weight in that goes into that neuron is trainable or not. This is helpful when we build up an arbitrarily complex network and we need to tell Keras to train the 5th weight in this layer, the 2nd weight in the 2nd layer, and so on. Having this list of flags helps us to decide which neurons to train easily. So let's just correlate this code with this picture once again. I keep going back and forth, but I think having this picture is helpful. What we've just done is built using the create node function, neurons A1, A2, and A3. And we just call those functions in the create model command to build all of these connections. So effectively, we are at this point in the network. So what we need to do now is just repeat that process and build up the output neuron. So we could just say output is create nodes with the inputs A1, A2, and A3. And that's kind of what we do, except that we explicitly spell it out again because we have a 4th input to consider. Remember the input ones that I brought up during the processing of the data set? The reason we have that extra input is so that that extra input can act as a bias to the output. So the entire reason we're having this entire code block is because we want the ability to say that the output is, well, it's some function of the inputs A1, A2, and A3 plus some bias term. And that bias term allows us to access more complex functions than we would be able to without the bias. So that's the reason for the extra complexity. That's the reason you're seeing this giant code block again. And we can walk through every line of this, but I'll assure you that what we have here is just an extension of what we've seen in the create node function, but with 4 nodes in the input. So we don't have AN1, AN2, AN3 now, we have AN1, AN2, AN3, and AN4. But the logic is exactly the same. So just as an example, what we're doing in this block is saying AN is some activation applied to AN1 plus AN2 plus AN3, sorry, AN3 plus AN4. The AN4 acts as a bias. So this is a lot to take in, but let me reiterate the key points. We are creating this network connection by connection, neuron by neuron. And at this point, we built neurons A1, A2, and A3. And we use the same logic to build this output neuron that we call out the output. So now what we can go ahead and tell Keras is create me a model where the inputs are input 1, input 2, input 3, and input 4. Input 4 is the list of ones. And the output is this output neuron that we painstakingly built, writing it out so explicitly. And given this model definition, we can connect it to an optimizer that helps decide how this model will be trained and define an error metric for the training, which is going to be the mean squared error. This is going to be the term that will help us compute the first term in the fitness of an individual, the error on data. So let's go ahead and run this cell. There's some other lines of code in that, but that's to help this process. So we're defining lists for bookkeeping and whatnot. That's not critical to our understanding of developing PNNs. What we then need to do is, having finally created this model, is to define how to train this. And we're going to use the model.fit command. If this is your first time training a neural network, I would recommend looking at some of the other sessions in this workshop, or looking at some of the other tools on nanoHUB that introduce you to simple examples of training a network. In this case, we've built a highly complex customized network, but the underlying logic is the same. We still pass in our raw data. This is where the data actually enters the model. Everything before this was just tensor operations. And we use the model.fit command to train the neuron for a certain number of epochs, which are loosely related to the iterations, but they're not exactly the same. So let's just go ahead and run this cell. And let's skip ahead to step 3, which is defining the objective function. We've set up our model, we've defined how to train the model, and we know how to compute the error that that model makes when making predictions. So all we need to do to define the fitness of that individual is add in that second term, which is the parsimony term. And that's what we'll do in this function called the objective function. And here's where we'll make the switch from working explicitly with neural networks, layers, and neurons to working in terms of the individual, which is that list of numbers that I talked about, which is the encoding of that neural network that will be used by the genetic algorithm. So we're going to take in an individual, which is a list of numbers in this function, and create a model using that. The create model function, as we just saw, takes in that list of numbers, knows which number corresponds to which activation function, builds the neuron appropriately, puts all of the neurons together, and gives us the model. So that's the job of the create model function. And what I'm going to skip ahead to is this evaluate command that evaluates this model that we've just created on the training and the testing sets. If we have any trainable parameters in the model, we're going to train it. Sometimes you may end up with models that have no trainable parameters. All of the weights are zeros or ones, in which case we wouldn't train it. There's a lot of other code here that seems like a lot to take in, and it is, but all of this is to check for outlier cases or weights where we mistakenly initialized one of the weight values to be 0, and we went into an inverse operation and gave us an NEN. So this is just avoiding those kind of errors. But if I draw your attention to this line here, this is the line that we wrote in the slide. So the objective function is the MSE test term, which is a logarithm of the MSE test, plus P, the parsimony coefficient, times an activation function score and a weight score. The activation function score relates, computes a metric given all the activation functions of each of the neurons, and the weight term computes the penalty for having trainable weights as opposed to weights of zeros and ones. So this is the equation or the line where we define what is the fitness for a given individual. It's going to be computed by this equation, and using this equation requires you to train the network and to compute this parsimony score. And just so we have a handle of what's going on, we're going to print the individual. Each time we evaluate an individual, we're going to print it, and we're going to print the objective function and all of the terms that went into it. So we can clearly see how different individuals are defined and how differing they are when comparing them to the data set. So let's go ahead and hit Shift Enter on this. I'm going to take a second here and pause and review what we've done because we're almost at the end. What we've done so far is read in our data set, build up this parsimonious neural network using two key functions, the create node and the create model. The create node builds up each neuron connection by connection, and the create model puts all of these neurons together to create this entire model, which we can then pass to Keras and say, here's my model, train it using this optimizer, using this error metric. And what we've then done is connected this training to the fitness function of that individual by collecting that MSE test term, the performance of the model on the test set, and a parsimony term, which comes from the activation functions and the weights. So I hope that's clear. There's a lot of code in this, and this might be a lot to take at first, but I hope that the logic or the workflow is clear. Because what we're about to do now is actually the exciting part. So what I'll actually ask you to do in this step is to go ahead and run all of the cells below here, because we're going to set up the genetic algorithm and it's going to take a few minutes to run. So let's go ahead and do that while we walk through what's exactly happening. So if you can just follow me and keep hitting Shift Enter till you reach the end of the notebook, you're going to see some stuff being printed onto the screen. These are some warnings about using, I guess, a slightly older version of TensorFlow. And eventually you'll start to see some prints about evaluating an individual, printing the objective function, and all of that. So I'll just wait for a second for you guys to run those cells. You should start to see some prints. If sometimes the kernels can be a little slow, so please have some patience. And while this runs, so here we go, we start to print something. We see some numbers here, we see an individual, we see an objective function. So let's try to understand what's going on here. So if you scroll back up to step 4, setting up the genetic algorithm, we've now defined how to encode a neural network as an individual and what the fitness of this individual is. That's what the rest of the notebook was. Now we're going to perform the genetic algorithm operations, which is exciting. And we're going to use the deep package for this. And the first thing that we're going to do is create this class called the fitness min class. The weight of -1, which is an argument, tells us that we want to minimize the fitness of our individuals in the genetic algorithm. If the weight was +1, you would say, I want to maximize the fitness. And the way we've set up the problem, we want to minimize the fitness, but you could set up the problem in any other way. What we're doing here is declaring a class called fitness min that we will then attach to each individual, as you'll see in a second. In fact, that's what the next line does. The creator.create command creates an individual class, which is a list of numbers, like I've been saying, but it's a list that has an attribute to it, an attribute that's called fitness. And the fitness is, well, obtained from this class, the fitness min class. Now you might be wondering, why is this so complex? Why am I going through all of this? It's because when we define these classes using the deep package, we can easily tell the deep package to say, perform a mutation without having to worry about swapping genes ourselves. So this slightly lengthy syntax is the cost we pay so that the genetic algorithm is easy on our eyes, easier to understand. So we use the creator.create to create our classes. We use the toolbox command to register a set of tools. What are these tools? These tools are going to be the crossovers, the mutations, and the selection processes that we use. This is the heart of the genetic algorithm. And what I'm going to draw your attention to is this toolbox.register command, which is saying I want to register a new tool in my toolbox. What is this tool called? This tool is called create individual. And all of the arguments after that tell us how to create that individual. So I told you that I want to have this network be represented by a list of numbers. And we know what this list of numbers should be. It should encode the activations and the weights. So how do we actually do that? We define this function that uses one part of the individual to set the activation functions, and the rest of the individual is used to set up the weights. So it's going to select a random integer between, let's say, 0 and 4, and that's going to describe the activation functions. And the other random integers will describe the weights. So that's how we create an individual. I'm not walking through the details of this function, but think of this line, the create individual line, as the line where we say, I want an individual to be a set of random numbers between 0 and 4 or 0 and 3. I hope that makes sense. If your genetic algorithm is much simpler, you don't have constraints on what the integers can be, you can just use a simple init repeat command and have this be much shorter than this. But our problem requires us to have bounds because, for example, we have defined the activation function scores to be 0, 1, 2. So we can't have a negative integer there. So that's why we have bounded values, and that's why we use these special functions. The second tool that we're going to register is called the population tool. And all that tells is repeat, well, there should be a comment, repeat the create individual command n times to create a population of individuals. That's why we pass in the create individual operation from the toolbox. And that's how we define the population. Now, where is n? How many times do I repeat this? We're going to specify that in a second. We're just registering the operations for now, and then we're going to initialize them with the appropriate values. So let's go ahead. So we already run this cell, so we don't need to run it again. And in the final cell of this notebook, we define the other operations that are of interest. Mating, which is the crossover operation. This is where the deep package really shines. We can just say, give us the 2-point crossover method. And that this line takes care of performing crossovers for us throughout the algorithm. It's going to identify a subset of genes, swap them over between two individuals, and based on how we've encoded individuals using the other toolbox commands, it's going to map it back to the neural network, which is going to call in the create node, create model functions, and train those models automatically. This is why we labored through the syntax of deep, so that we can write this line here and be done with crossovers. And the same for mutations. I want to randomly flip an individual. I'm going to register an operation called mutate, and it's just going to perform mutations for me throughout. The other key tool that we want to register in the toolbox is the selection. How do we select fit individuals? We're going to use a tournament selection with a tournament size of 5. What this does is it selects 5 individuals from the population and selects the best one from it. And it's going to repeat this process till we have 5 individuals. So think of this as selecting a way of selecting the best k individuals from a population of n. And lastly, the most important aspect is connecting the objective function that we define to an actual operation in the toolbox so that the crossover and the mutation and the selection algorithms have knowledge of these fitness scores. And we're going to do that by registering an evaluate toolbox, a tool in the toolbox. So this is the heart of the genetic algorithm. This is where we define how crossovers are going to be done, how mutations are going to be done, how do we select fit individuals. And what the rest of the code does is initializes the population and runs the genetic algorithm. And really, that's just 2 lines. There's a lot of code here, but let me point out the 2 important lines. The first line is this. It says, give me a population with n equals 5. So give me a population with 5 individuals. And because we've painstakingly described each of the operations, we can just write this line and be done with defining a population. And the second line that I want to draw your attention to is this last line, which calls EA simple from the algorithms module of deep. And what this EA simple does, it uses all of these tools that we've registered in the toolbox to use a population, perform crossovers and mutations, evaluate using the objective function, and select some individuals using the tournament selection to give us one generation. And then repeat that for another generation, and to go on and on for how many other generations we want. So all we need to do to write our genetic algorithm is to just call this function. And in that, we've set up the genetic algorithm. So a lot of the work in this notebook was to relate the neural network to the genetic algorithm. The GA is done using deep conveniently. And I noticed that for me, at least, this cell has run. For some of you, it might still be running, depending on how slow or fast the kernels are. But what we've done here is run a toy genetic algorithm problem where we have 5 individuals in our population, as we saw in this line, and we run 3 generations. And what we're going to see is a lot of things being printed on the screen. We've seen a list of numbers, which actually are the weights of that model. The individual that is responsible for having those weights, and the objective function or the fitness of that individual. So if we focus on the first individual, the terms in the objective function include the MSE test term, the activation function score, and the weight score, which are then all combined to give us this final score of 3.37. This is the fitness of that individual. The next individual is not as fit. Remember, we want to minimize fitness. So this has a score of 13. So it's not as good. And we repeat this so on, and every so often we're going to get summaries of an entire generation. And what we're going to see is that in this generation, we evaluated 5 individuals, and the first individual actually turned out to be the best one. And this is going to repeat for many other generations, and we can post-process this output and make it look nicer, but that's not of our interest for now. At the end of 3 generations, what we have is some individuals that perform much better than the others. So in the remaining 2 minutes that I have, I'm just going to quickly demonstrate how we can go from discovering this individual to actually writing down an equation and arriving at our end result. And to do that, what I've done is put together this second notebook called Evaluating a PNN Model. This is the 5th notebook in the landing page. And this contains almost exactly the same code as in the discovery process, except that we use the SymPy library, SYMPY, to connect a list of weights and activations to an equation. If I just go ahead and hit run all, I've already pre-populated it with the best individual from this run. And what we're going to see at the bottom is this parity plot that shows how the model performed. So from this toy genetic algorithm run, what we found was that the best model does pretty good on the training dataset in blue and the testing dataset in orange. There is an outlier point, but by and large, the model performs well. And as of our main quantity of interest, the equation, we can actually scroll up here to the cell which uses the SymPy commands, and we see that the equation is that the normalized output is some constant times theta t prime plus some other constant plus another constant divided by theta 1 prime. And when we write this down on a paper and convert all of the normalized quantities into non-normalized quantities, what we actually see is that we have discovered in this slide PNNC, which is this point here in pink. And by varying the complexity, the parsimony coefficient, we can get various models. And I'll leave that as an exercise to you. Just as a side note, the other notebooks in that tool, if you're curious about what they do, they help set up this process to discover integration schemes for data, where we learn the position overlay integration scheme directly from data. So if you're interested in that example, go ahead and check that out. But I think I've taken my entire 1 hour, so I'll stop at this point and be happy to answer any questions. Thank you.
So thank you, Saaketh. This is a really nice presentation. And we appreciate the effort in cramming so much information and hands-on activity in an hour. I know it's challenging. So we're running out of time for questions, but let's stay for 1 or 2 more minutes if you guys can, and see if we can answer some. So one of them says, and I tried to answer a few, will we have access to the code discover _melting .*? So is that code part of the tool?
If you look at the landing page, and if you're interested in how this landing page is set up, you'll see what each of the links, which notebook it takes you to. So if you're having access to discover_melting, that's actually the notebook that I spent most of the time on. That's where I just set up deep and the PNNs to perform the discovery process. So that notebook is that notebook that we've used for the entire.
So that's there.
Yep.
All right. There's another question. Are there restrictions on the values for CX, PB, and mute PB probability, and the cross-link probability and mutation probability? And the answer is yes. Of course, you control those.
Correct.
Right, as part of the genetic optimization. You
Exactly.
can even change them with generation. So you start mutating like crazy to explore space, and then you hone in on the best performers. So
exactly.
absolutely, it's actually important to use reasonable values. Any other questions? And now feel free to unmute yourself and ask the question if you would like to jump in. And I guess, let me clarify the question. It was from Bobby, and he's saying, are there restrictions on the values for cross-link probability and mutation probability?
Well, those are probabilities, so they have to be between 0 and 1. But beyond that, any other constraints come from, there's no official constraint, but beyond that, it becomes a question like you were mentioning of how often do you want to mutate and generate random new individuals versus how often do you want to perform crossovers and stick with your initial gene pool and perform swaps in that. So a high mutation probability will give you an opportunity to discover interesting individuals that you never had in your initial population. So that's why a high mutation rate could be used. But there is no restriction on that. It has to be between 0 and 1. That's all, because it's a probability.
Yeah, and I think it's good for your problem to explore a little bit with probability, mutation probability, crossover probability, and also these tournament sizes that tells you how much, what probability of keeping the fittest individuals you have from generation to generation.
That's right. Yep.
Let's all thank Saaketh one more time. Well done.